All right, good afternoon, everybody. Hope everyone had a good weekend. A couple things before we get started with today's lecture is, first of all, hopefully you're all aware that we're having quiz 2 on Friday. There's a quiz review tonight. It's from 7:30 to 9 in room 10250. Okay, so we're going to go over two different topics in today's lecture. The first is we're going to continue a little bit with what we were going over in last lecture, which had to do with how do we implement procedures on our beta. And we're going to go through a detailed example of, what is it that exactly that an image of a stack and a particular program is telling us and how we would go about analyzing it. And then we're going to talk about the notion of computability. Okay, so we ended off last lecture with this slide here, which talks about which has the factorial program written in C, and it's translated into our beta assembly. And we pointed out that there are a few important sections to this code. So the first is our entry sequence over here, where what we're doing is we're always following the convention that we're going to push our linkage pointer, push our base pointer in order to save these registers. Then we're going to make the stack pointer and base pointer point to the same location on our stack. And next we're going to save any registers that we're going to make use of. In our exit routine, we're going to do exactly the reverse of this. So we're going to pop R1 in order to restore the value of that register. We're going to move BP to SP. We're going to restore our base pointer, restore our linkage pointer, and jump to the linkage pointer to get back to wherever we were called from. And then over here in the middle, we had this recursive call, where after computing the new argument for factorial, it pushes that argument onto the stack and then branches recursively to this factorial program, saving the return address in the linkage pointer. And then when it returns, it takes that pushed argument off of the stack. So if we look at this structure, there are a couple things that we want to pay close attention to. The first is that when you have a recursive procedure, every single time you call the recursion, you're going to have what's called an activation record. The activation record is going to have exactly the same structure. So in this particular example, we have our argument, which was pushed on by whoever called the factorial program. And then we put onto our stack our linkage pointer, our base pointer, and our saved R1 register. Every time we call factorial recursively, we're going to put another activation record with these 4 elements onto our stack. So, just a couple things before we move on from this slide is I just wanted to make it clear to everyone that this push R1, which saves register R1, corresponds to this pop R1, which is where we're restoring the register. In our recursive call, we also have a push R1 where we push, in this case what we're doing is we're pushing an argument. It's not a register that we need to restore, so we're not actually restoring this value. Instead, we're simply deallocating it in order to make our stack go back to its original state before we called this function recursively. All right, so let's take a look at what our stack is going to look like when we implement this factorial function. So suppose that I call factorial with the argument 3. So what's going to happen is I'm going to put my argument 3 on my stack, and then when I enter factorial for the first time, I'm going to save the LP register, save the BP register, and then I'm going to save the original value of R1 so that I can later restore it. Factorial of 3, we saw in last lecture, depends on factorial of 2. And so it's going to create another activation record on our stack. And here we have argument 2 with its own versions of LP, BP, and R1. Similarly, factorial of 2 depends on factorial 1, and factorial 1 depends on factorial 0. So at some point in our computation, we're going to have all of these activation records stored in our stack. And then when we're ready to start returning values, we're going to deallocate these activation records in reverse order. So one important skill for everybody to have is to really be able to understand the structure of a stack trace. So if I give you a program like factorial, and I give you a portion of a stack, you want to be able to make sure to correlate which pieces of the code go with which pieces of the stack. And so that's what we're going to go over today. And in particular, this is something that you'll find very useful for 6004 quizzes, so hopefully you will understand it after the next few slides, as well as what you did in recitation. Okay, so what kind of information do we have on our stack? The first thing to recognize in our stack is the BP links, okay? So your base pointer is always pointing to the location immediately following the saved BP, okay? And so initially when you start off, you have your base pointer pointing to this yellow saved R1 location. Then when you go to call, you know, the next recursion of fact2, you have a BP that's pointing to this location, and so on, okay? So what that means is that this saved BP over here is going to be the address of this location over here. So you can see that better with these arrows. So essentially what we're saying is that this location, which was the base pointer of my previous call to my factorial function, is going to get stored over here. And so this structure is always going to repeat itself in every single beta program that we write, okay? So it's important for you to be able to recognize, okay, where is my base program showing up in my stack trace, and what information can I gather from it? So suppose, for example, that I told you that the address of the first base pointer was 0x10c. Well, what could you infer from that? You could infer a few things. The first is I would know that this location in my stack has the value 0x10c. Okay, so even if I didn't tell you that, you could actually tell me yourself that that's the value of that element of the stack. Another thing that you know is that each of these locations takes up 4 bytes. So if this address is 0x10c, then I can figure out that the next address is 0x110, then 114, 118, 11c, which means that my next BP is going to have this value of 0x11c. And so what that tells me is that over here, in this green location, the value that's going to be stored for the base pointer is that 0x11c. And so you can continue in this manner in order to answer questions like, what's the value of the current base pointer, okay? And so even if you weren't, shown that the base pointer is pointing to this location, you should be able to figure out by simply having seen, this original value of 0x10c and the code itself, which gives you information about what your activation record looks like, that ultimately, once you get to this activation record, your base pointer is going to point to this location, and that will happen to correspond to address 0x13c. Okay, so that's an example of what information you can infer from your base pointer, the different values of the base pointer in your stack trace. Okay, how about the linkage pointer, which we're saving in every activation record? So what does the linkage pointer represent? It represents 2 things. We have our original call to factorial from our main program, and we have the recursive call to factorial within factorial itself. So suppose that the address of this original call was 0x14. The value that would get stored in this linkage pointer is the value of the address of the instruction immediately following this, which is 0x18. So when I'm calling branch factorial from my main routine, my LP is going to have a value of 0x18 put into it. When I call it from over here in the recursive call, the value that's going to go into LP is 0x60. Okay? And so we want to be able to recognize these different values of LP on our stack trace in order to determine which corresponds to the call from the main procedure, which corresponds to recursive calls to our function. So if I show you this stack trace over here, we see that we have two different values for our LP register. Here we stored the value 0x18. Here we stored the value 0x60. 0x18 was the one that corresponded to our main subroutine. 0x60 was the return address from within our factorial function. And so what this allows me to answer is, for example, if you were asked the question, what's the address of your original branch instruction? Well, you have enough information on this stack to figure that out, okay? You know that 0x18 is the return address from the original branch instruction, which means that the original branch instruction was one instruction before that, so it was at address 0x14, okay? Similarly, if you were asked, what's the address of the branch instruction of within the factorial procedure? Same kind of thing. You would need to recognize that in that case, your return address is 0x60, and note that that repeats itself as you do multiple instantiations of the activation records. And so the branch instruction occurs one instruction before this, and so again, you can simply subtract 4 from 0x60 to determine the address of the branch instruction within your factorial routine. And another example of something you might be asked is, well, what's this value that's missing right here? And it should be very clear at this point what that is, and can anyone tell me what it is? 0x60, right? It's just the same value that we are storing every time through the recursive call, okay? So you want to recognize that in general, assuming you only have one main function and one subroutine, you're going to have two different values of your LP, and you want to recognize where they occur in your stack trace. You may have more than two if sometimes you're calling a procedure more than once. That does happen, so you want to become familiar with that as well. But in this example, we're just calling factorial once within our recursive procedure. Okay, so what are a couple other things that we want to be able to answer from this stack trace? Suppose that I give you, this arbitrary looking stack trace, and I tell you that I got this from running factorial on n, and I happen to stop my computer when the PC was at address 0x40, okay? So I'd want to be able to come in here and identify different portions of my stack trace. So for starters, if I was asked, what's the argument in the current or active call to factorial? How would you go about doing that? Any ideas? Yeah. Say that again? Two little squares above BP. Exactly. And so what we would do is we would label this current activation record. And so we know that our activation record consists of 4 words for this factorial program. We've got our argument, our LP register, our BP register, and the saved R1. And that means that the argument is 3 locations from above this BP, which is going to be this value 3 right here. So the argument to our active call to factorial is 3, okay? Similarly, if you were asked what's the argument to the original call to factorial, how would you figure that out? Any ideas? Yep. So you want to be a little bit careful about that, which is that the top of what you're shown in your stack trace is not necessarily correspond to the main program, okay? So you want to actually identify all of the activation records, right? I mean, we may try to confuse you by putting some additional words even before here that have nothing to do with a call to factorial. So what you'd actually want to do is you work your way backwards, right? So we know that base pointer is currently over here. And so this corresponds to one activation record. Then the next 4 bytes are the next activation record, and so on and so forth, okay? And then if we analyze this further, looking at the values of the linkage pointers that appear here now that we've actually identified our activation records, well, we see that we have 2 distinct values for our linkage pointer. We have 40, that's stored here, here, and here, and we have 80 that's stored up here, okay? The fact that this value is different from the others means that this corresponds to the original call to factorial from my main program. Yes?
So can you explain how you split them up into like each of the recursive like substacks? And my specific question, like those bottom 5 elements that correspond to the current recursive call, like there are 5 elements there, but all of the previous like subsets only have 4.
So this actually only has 4 as well. This blue is a little bit hard to see. This 2 actually corresponds to the next activation record. So what you have to remember is that your base pointer always points to a particular location in any activation record. So for example, suppose that I actually had a function where I wanted to make use of registers, you know, R1 and registers R2. Then my activation record could look something like, here's my argument n, then I'm going to have my linkage pointer, then I'm going to have my base pointer, then I'm going to save R1, and then I'll save R2. And so my activation record is actually going to be of size 5. But the key is that that size repeats itself every single time. In this particular example, this is what our activation record looks like. And we also know that for each activation record, the base pointer points to the location immediately following where the base pointer was stored. Okay, so if I'm told that the base pointer is pointing to this location, I know that what's right above it is the previously stored BP value, is the value of the BP that we had previously. Okay? And so then from then on, you can work your way backwards.
So in this example, like, would you actually figure out where 12C is in memory, and that's where you draw that arrow for the previous base pointer? Or did you use like the prior knowledge that you were only using a single register?
I used the prior knowledge that I was only using a single register. And so my activation record has 4 elements in it, which means that each one of these is also going to have 4 elements in it. But that being said, now that I've actually identified my activation records, that does actually give me information about the address of these different memory locations, right? And so in fact, the address of this location right here is 0x12C, and so on. Any other questions? Okay, great. So if we want to answer this question of what's the argument to our original call, right? What we had to identify was that we had 2 different values of LP, this 40 and 80. You can assume that all of these values are in hexadecimal. You'll be told that if this was to appear on an exam. And so this corresponds to our original call of factorial, which means that the argument of the original call was 6. Okay. How about trying to answer the question, what's the location of the original branch instruction? Again, now we know how to do this, right? We know that this is the address of the return address from the original branch instruction, which means that the original branch was 4 bytes before that, or in other words, 0x80 minus 4, which is 0x7c. Okay? Now, next question is, what instruction is about to be executed? Okay, so what do we need in order to figure this out? So first of all, we're given information about the value of our PC here, okay? We're told that the PC is currently at address 0x40. 0x40 happens to also be something that we know something about, which is it's the return address of the recursive calls to factorial. So if I go back to my program, what I know is that this instruction immediately following my branch is at address 0x40, which means that the instruction that I'm currently at is the deallocate 1 instruction. Okay, everybody clear on how you figure that out? Good. And just a couple other types of questions that you want to make sure you can answer is, suppose we ask you, okay, what's the value in R0? Well, looking at our code, you know, and knowing in general that we store the result into R0, we should be able to figure out what's currently in R0. Okay, so we already figured out that we're currently in the call to factorial of 3. So what do you think might be in R0 at this point? Any ideas? So is it the result of executing factorial of 3? Yep.
It's the result from executing factor 2.
That's right. Why is that?
Because you're now moving on to 3.
Right. So you have to remember where you're actually currently in your code. Okay, so we just identified that we're at this deallocate instruction, which means that we have not yet executed this multiply instruction for the instance of factorial 3. So what's in R0 is what was returned from having called factorial of 2. Okay? And so eventually that's what's in this R0 right here. Eventually you're going to take that, you're going to multiply it by R1 in order to ultimately end up with R0 having a value of factorial of 3. But at this point in time, what's in R0 is the answer for factorial of 2. Okay? And finally, suppose that I asked you what's the value in your BP register. So again, following the logic that we talked about earlier, I can figure out things about the address of the BP, right? So I know that this address 12C corresponds to this location right here, and so I can simply start counting from there, adding 4 bytes at a time to figure out that the current value of my base pointer is 0x13C. Okay? Similarly, the current value of my stack pointer, which happens to be 2 locations after the base pointer, is just going to be 8 more than that. Okay? So what it actually has happened here on the stack, if you go back for a second to our code, right, given that we're here, what we just did is we've pushed R1. We've pushed the argument for our next call to factorial, which is why the stack pointer is now 2 locations away from our base pointer. Okay? All right, and finally, if I was to ask you, can you determine the value of these locations? Any ideas whether we can or not? I see no's, so why no?
You don't know where the original factorial is called from?
Mm-hmm.
So
Correct. So this corresponds to our initial activation record. So we don't know what value was in this R1 that we, when it was being used in the main program. And we also don't know what the previous value of our base pointer was. Okay? All right. So that should give you, hopefully, a good sense for how do you go about interpreting what's given to you when you're given a stack trace and a piece of code. All right, now we're going to move on to our next topic, which is universality. So if you recall, when we were studying about Boolean gates, we spoke about the concept of universal gates. And the idea there was that a gate or a set of gates is universal if it can be used in order to perform any Boolean logic function. And so we found that, that things like NAND are universal. You can use NAND in order to create any Boolean function. We also found that NOR is universal. Similarly, you can take an AND and a NOT, or an inverter, put them together to create a NAND, which means that AND with NOT together is also a universal set, and so on. And so today we want to take this a step further, and we want to ask ourselves, what makes an actual instruction set architecture universal? And so specifically, we want to be able to answer these types of questions. What kind of problems can we actually solve with this von Neumann computer model that we came up with, or our beta in the specific example? So, can it solve everything that a finite state machine can solve? Can it solve any problem that has an answer? Does it depend on what instruction set architecture I use? In order to be able to answer these questions, we have to have some kind of model. We call this the model of computation of what exactly can and can't be computed by my particular instruction set architecture. Okay, so in the roots of computer science, there were essentially many models of computation that were suggested that could basically represent all computations that could be performed. And one of the goals of this universal model was to identify, a model that could actually perform all possible computations. So far, we've studied about FSMs. Okay, FSMs are quite capable. They can do a lot. So let's consider for a moment whether an FSM might be this ultimate computing device. Can it actually solve all of our problems? Well, if you recall from Lab 2, what we learned is that an FSM actually, while it can do a lot, it actually has some limitations. So specifically, there are certain problems that it can't solve. For example, if we wanted to create a parentheses checker, where we wanted to be able to identify whether, given a particular input, is it a balanced set of parentheses or not, an FSM can't actually solve this problem for us. The reason that it can't solve this problem for us is because in order to actually answer this question, you need to keep track in your FSM of how many left or open parentheses you've seen so far. This is basically counting. In an FSM, you're limited in terms of how high you can count by the number of states that you have. So essentially, the answer is no, I cannot solve this problem with an FSM. And the main issue with FSMs is that, regardless of how large my FSM is, I can always come up with an example that this FSM can't solve. So we want to find another model which is even stronger than our FSM in order to be able to solve all computable problems. So Alan Turing provided us with such a model. The model is called Turing machines, is a Turing machine. And basically the way that this model works, again, you should be familiar with this from Lab 2, is you have an infinitely long tape here, which holds on it symbols that represent the input to your machine. And then you have a finite state machine that specifies what transitions you should make based on the inputs that you see and what you should write on the tape as a result. So, the benefit of Turing machines is that it essentially gives you a mechanism for taking any integer input and identifying what the integer output of it is. And so the way that we do that is we model Turing machines as an integer function as follows. Essentially, you first take your input tape and at some point your input is going to end. So let's say, it is of bounded size. So I can encode every single symbol on my tape in as a, as an encoding of, so let's say I have, 4 symbols in my tape. I could encode each of those symbols using, 2 bits. And so then I could go through and let's say I start at my head, my 1 would be represented, let's say with 0, 1. This 1 would be again 0, 1. And you can go back and forth around the head, storing all of your inputs until, and concatenating them into one big long integer, which represents your entire input, okay? And so I can use an integer to represent my entire input tape. Similarly, I can use a big integer to represent my output tape, okay? So far we have managed to figure out a way of making both our inputs and outputs be represented as integers. Now our FSM here is basically the brains of this machine, and it's telling you, based on the state transition diagram, what to do for any given, symbol that it sees on the tape, what it should write on the tape, and which direction it should move. So you can imagine taking this state transition diagram, and it's really just a truth table that's defining what it is that the behavior should be. And if I was to enumerate every single possible such truth table, and then associate an index with each one of those enumerations, then what this allows me to do is to say something like, okay, Turing machine of, where the FSM's enumeration happens to be index 347, if I give it an input of 51, which is my encoding for my input tape, then I will produce an answer of 42, which is the encoding for my output. So in other words, we've defined our Turing machines to basically be a function of integers. So specifically, it's what this is saying is that Turing machine I, which happens to be 347 in this example, given the input x, which is 51 in this example, is known to produce the output 42. Okay? And so this gives us a way of thinking about our Turing machines as integer functions. Now, in addition to Alan Turing, who came up with this model of computation of Turing machines, there are a number of other people who worked on different models of computation. And in fact, there were many models that were identified that worked equally well. So there was, in fact, all of these people actually worked together, and Kleene and Post and Turing were all students of Alonzo Church in Princeton University, and they all worked on this same idea of what's the best way of modeling computation. And specifically, they were interested also in identifying what are the types of problems that cannot be modeled. In other words, how to identify what's not computable. Okay, so what's interesting is that even though each one of these guys came up with a different model of computation, it actually turns out that the problems that each of these models was able to solve was exactly the same. Okay, and the way that they proved this is that they basically defined transformations that turned Turing's representation of a problem into Kleene's representation of a problem. And so they were able to show that no matter what, any of these representations is the same. Okay, so the first thing that they identified is that, well, computability is independent of which scheme you're choosing for modeling computation. And what this led to is Church's thesis, which basically says that every discrete function is computable by any realizable, that is computable by any realizable machine, is computable by some Turing machine. Okay? So specifically, if we look over here, what this says is that if you have a function f of x which is computable, then there exists some Turing machine k, which given the input x will produce the output f of x. Okay? Now, this this theorem has actually never been proven, but it is universally accepted to be correct. So, we've now established that Turing machines are basically the model we're going to work with, and they can model any computable problem. Okay, so, I can have a Turing machine that knows how to do multiplication. I can have another Turing machine that knows how to do factorization, and so on and so forth. But obviously this, by itself doesn't look that useful, because ideally I want to have a machine that can do all of these things together. Okay, and so this is where the notion of universality comes in. Okay, we want to identify whether or not there is a universal function, a universal Turing machine. Does such a thing exist? Okay, the way that a universal function would be defined is that given inputs k and j, you would want to be able to emulate Turing machine k running on input j. Well, it turns out that U is in fact computable, and in fact you don't actually need very much in order to create a machine that can compute all computable functions. And so the way that we represent this universal Turing machine is that we have our input k, which identifies the machine itself. We have input j, which is identifying the input, and then that translates to, it's going to basically emulate what it is that Turing machine k would do with input j. And in fact, it turns out that there are infinitely many universal Turing machines, and so we can actually use any of them in order to perform any computable function. And in fact, our beta turns out to also be a universal Turing machine. And the criteria for determining whether or not something is universal is actually quite simple. All you really have to do is be able to support some basic functionality like conditional branches and some ALU operations. So specifically, what's going on over here is that you can think of k as encoding a program. Okay, so it's providing a description of what it is that your Turing machine will do, and j is your input. And so your universal Turing machine is going to interpret this program, and it's going to emulate exactly what Turing machine k would do on this input j. So this idea of interpretation is really one of the fundamental notions of computer science, which is that you can pass as an input a program which describes what it is that you want to do. And so, so basically what we want to ask ourselves for any machine that we're building is it a universal Turing machine? And how would we answer that question? We would answer it by showing a mechanism in which we can convert it to a previously known universal Turing machine. Okay? And so it turns out, as I mentioned, that you actually don't need very much in order to be a universal Turing machine. All you need is to be able to execute conditional branches and some simple arithmetic. There is one caveat, however, which is that in our processors that we build, we don't actually have unlimited memory. Okay, and so in order to really have that unlimited, unbounded tape of a Turing machine, that assumes you have unlimited memory. In the case of our CPUs, it's not the case. We actually have a finite amount of memory. But what we can show is that given a limited input size problem, then our machine can actually compute the result of that problem as long as the problem isn't so big that it doesn't fit into our memory. Okay? And so we're willing to deal with that caveat of having finite memory for our universal computer. Okay. So we've basically, shown here that one of the key ideas in computer science is that you want to be able to take a description of a program and translate it or interpret it into something that can run on your own machine. So for example, we might have a program that's written in C or Java, which it doesn't really know anything about the actual processor that you're running on. And you can translate that by running a compiler into a program, let's call it PY, which can run on your beta. Okay, we've seen how to do this already for our beta. And so this is kind of one of the main ideas in computer science, which is that let's build, something small, and with that we can build larger, more complicated things. So if, for example, I have a function q of x that I've defined, I can then go ahead and define a function p, which makes use of this previously defined function q of x. Okay, similarly, G can make use of H and P, and then I can make things that are more and more complicated by using these small building blocks. Okay, and by having this notion of a compiler, which can take, a high-level language like C or Java and convert it to assembly, which runs on my processor, we're able to have parallel paths where, on one hand, we're working on programming languages that will identify what's the best data structure to use for my particular problem. Then on the other hand, we have our hardware, which is working on different implementations of processors. And the idea is that regardless of which of these processors here I'm running on, I am using, I can take any of my high-level language programs and ultimately run it on that hardware. Okay, so just before we finish up for today, we've talked so far about what is computable, okay? And so we identified the universal Turing machine, and we talked about the fact that a universal Turing machine can be used in order to solve any computable function, okay? So given an input, an integer input, it can figure out what the integer output is for all computable functions. But the question still remains of, well, are there some functions that are uncomputable? And it turns out that there are. So if you can't actually come up with an algorithm that will solve a particular problem, then we consider that to be an uncomputable problem. And it's not that we don't know what the algorithm is. It's actually that there doesn't exist an algorithm that can actually solve these uncomputable problems. So the most sort of well-known uncomputable problem is the halting function. The way that the halting function is defined is as follows. If you have f of h, which stands for halting function, which receives inputs k and j, the way that this machine is supposed to work is it should generate a 1 if Turing machine k on input j is going to halt, and it should produce a 0 otherwise. So the idea is, can you create a machine that's going to determine whether Turing machine k is going to halt on input j? And it turns out that this is an uncomputable function. And the way that we prove that it's uncomputable is by assuming for a second the reverse. So suppose that I actually say that, that the halting function is computable, okay? If it's computable, then what we've learned today is that means that there exists a Turing machine, let's call it T of k, which given an input j can determine whether or not my machine is going to halt, okay? And so my description of this Turing machine H is that given k and j, it'll produce a 1 if Turing machine k on input j halts, and 0 otherwise, okay? And for a moment, we're just going to assume that we can actually build such a machine. Well, if I can build such a machine, then that implies that I can also build this Turing machine T of n stands for nasty here. And the way that I would build this is I would basically feed an input x as both my k and my j inputs to this Turing machine H. And what's going to happen, what I want to have happen, is that if the output of Turing machine H is a 1, then I want this Turing machine N to loop. If the output is a 0, I want it to halt. So in other words, I want it to do exactly the opposite of what TH did. Okay? So if I actually have a computable machine, T of H, which can tell me, you know, it can produce a 1 if TK halts and a 0 otherwise, then it should be fairly easy for me to produce this machine, which just does the opposite. However, what happens if I make x be equal to n? If I make x be equal to n, then what is this telling me? This is telling me that this Turing machine n of n is going to loop if Tn of n halts, and is going to halt if Tn of n loops. So it's impossible for me to both loop and halt on the same input n, and so I've reached a contradiction. So the fact that we've reached a contradiction basically tells us that our initial assumption, which was that we could build T of H, was false. And so T of H, which is the halting function, is not computable. Okay? And that's it for today. Remember that there is a quiz review this evening, and that the exam is going to cover lectures 6 through 12.